In example 1, we're modeling world population with the law of natural growth. Assuming that the growth rate is proportional to population size, we're using the data in Table 1 to model the population of the world in the 20th century. What is the relative growth rate? And how well does the model fit the data? Now we measure the time t in years, and we're going to let t equal 0, which is in the year of 1900. So that's the first year that we're looking at, so therefore that would represent the initial time, which is why we're letting t equal 0. Now we measure the population p of t in millions of people. Then the initial condition is p of 0, which represents 1900. The population at that time was 1650 millions. Now we are assuming that the growth rate is proportional to population size. So the initial value problem is the following: d of p over dt, which is equal to k times p. And now we have an initial condition here at p of 0, which is equal to 1650. And so from equation 2, which is y of t, which is equal to the initial y times e to the constant k times t. So p of t is going to equal 1650 e to the kt, since 1650 represents the initial population. Now, one way to estimate the relative growth rate k is to use the fact that the population in 1950 was 2,560 million. So therefore, we can say that at p of 50, then this function 1650 e to the k times 50 is equal to 2,560 million. And then that's going to allow us, so we can pick any point we want on that table, allow us to be able to solve for the constant k. So now we have e to the power of 50k, dividing both sides by 1650, so we have 2,560 divided by 1,650. And then what we're going to do is we're going to take the natural log of both sides. So whenever we solve this scenario, we take the natural log of e to the 50k, and that's going to equal the natural log of 2,560 divided by 1650. And so then we would get 50k, which is equal to the natural log of 2560 divided by 1650. And then dividing both sides, we get 1 over 50 times the natural log of 2560 divided by 1650. So that's going to allow us to be able to find the constant. So k is going to equal approximately 0.00878. If we change this to a percent by moving it over 2 decimals, then we would say that the relative growth is about 0.88% per year. And then the model is going to look like the following. We're going to have p of t, which is equal to the initial population, 1,650, e to the constant now, which is 0.00087846 times t. So now in Table 2, in Figure 1, allows us to compare the predictions of this model with the actual data. So you can see that the predictions become quite inaccurate after about 60 years. So after about 60 years, you can see that here is this function, and then here is the actual particular output value of each of those years. So now if we look at Figure 1, we might think that we could get a better model by using the given population for 1970 instead of 1950 to estimate the value of k. So what we can do there is then we're going to get p of 70, which is equal to, again, 1650 e to the 70k, which is equal to 3,710. And then we're going to divide both sides by 1650, and then take the natural log like we did up here. And then we're going to get the constant now to be approximately 0.115751. And now the estimate for the relative growth rate is now going to be 1.16% per year. And now we have this model. And so in Figure 2, it's going to illustrate the second model. And this exponential model is more accurate after 1970, but less accurate before 1950. So now you can see that this particular graph closely resembles the actual values, the inputs and outputs.